Hello everyone, May the 13th. Alrighty, let's do this. Count ways to build good strings. I think this is one of the ones I solved for fun. Alright, given the integers 0, 1, low, high, you can construct a string by starting with an empty string and then at each step perform either of the following. Append the character 0, 0 times. Append the character 1, 1 times. This can be performed by any number of times. A good string is a string constructed by the above process, having a length between low and high, inclusive. Return the number of different good strings that can be constructed, satisfying this property, and we have the mod. Okay, so low is 3, high is 3, which means you can append 0, 3, 1 time, 1 time, and you want to make it to be 3. 3 to 3, so it's only 3. There are 8 ways. And 2 and 3. For 2, we can do 1, 2 times. 0, 1 time, 0, 1 time. 2, or this. Okay. Low and high. From low to high, between low and high, should we say how many times you can do? Let's see. You can do 0 some number of times. All right, you can do 1 some number of times. That's let me see. So you have the limit, right? You have the limit from low to high. So we can say your first attempt can be either 0 or 1. All right? Index. The current index. So we start from 0. So we're saying if you start from 0, how many different ways you can make, okay? And if you start from 1, how many different ways you can make? You start from 2, how many different ways you can make? So we can start from 0, right? We say dpi is the number, okay? The number of ways to construct the string from position I to the end. Well, what is the end? We don't know. So let's say, well, def dp. Yeah, I like to say index. Okay, so this one return an int. So what do? Well, we have low and high, so we have to keep adding until we hit high, right? And it has to be so the end will be if, let's say, index is larger or equal to high, right? That will return 0. Otherwise, we always try, right? We always try. So we can try, we can say, try at 0. We can add 0. Right, that's one way. Or we can add 1. Okay, if we add 0, the index will move down that many times. So option 1 shall equal to dp. We add 0, should be index plus 0. Okay, because if you add 1, 0, you add 1. Or option 2, right? Option 2 is you add 1. So you either add dp or you add 1. So you say index plus 1s, right? So we try add 0, we try add 1 at a current position. Okay, then what? Then we say if this add this, it's too much. That means we cannot add. Or option 3, we do not add. If we do not add, then index has to be larger, because low is 2, so 0 index. If an index current is 1, so it should be larger than, larger or equal to low minus 1, right? If it's larger than low minus 1, then it works. That's option 3. We just terminate right here. So we can say let's return the 3 options. Option 1 plus option 2 and plus option 3. Let's give this a shot. Collections, func tools. Okay, dp index, return index int. Index is larger or equal to high, return 0. We need mod. Okay, so option 1 is dp index plus 0. Option 2, I mean, probably can just go return this plus dp index plus 1 plus dp index, no, int index larger equal to low minus 1. And all of this need to mod. And I'll return dp 0. dp 0. Let's see. So we have 3 3 1 1. Shall give us 8. 2 3 1 2. Shall give us 5. Low, high, 0 and 1. All right. Okay, let me think what went wrong. Oh, this is actually not right. Index. No, wait, hold on. This is right. Index is larger or equal to low minus 1, right? So low is 3. So we start with 0. This is false. We cannot just do nothing, right? Because index is 0. Index is 0. That's not right. That's not right. So we're trying to fill 0, right? But we cannot just fill 0 by itself, right? So we either fill this or fill this. And the current index after we fill, so we start 0 is we start filling from this position. We start filling from 0 position, right? And then we fill 1. Yeah, you haven't filled it. You did not fill it. You need to fill it first. So I can say we cannot not fill, right? So we fill it, right? And then we fill this. We fill 0, so we have something, and then we say what's gonna happen next, right? Hold on. Let's say filled 0. Okay, we can say j shall equal to index. Let's say m, and then m equal to index plus 0. Okay, and if res, we can say res equal to 0. So res shall plus equal to m is larger equal to low minus 1, right? Because that's if we don't want to continue filling. And res equal to res plus dp m. This is after we fill this, we continue filling, right? Then we say fill 1 n equals index plus 1. Res plus equal to int n large equal to low minus 1. This is not filling, and we need to keep fill n mod. Right, now we should return res. This one, right? Now it's too much. Damn it. Oh. Hold on. We start at 0, right? We can fill some, and then we start from this. Hold on. We start filling from this. Okay, so we want to know how many different ways we can fill. That is just if that's going to be 0, okay? So as long as we can fill, we shall try to fill, right? Because the current position is nothing, so we always say, I want to add this, right? We want to fill this. Because at this position, I can either fill 1 or I can fill 0, right? So after I fill 1, I have this number of ways. If at this position I fill 1, okay, I fill 1. Then I want to know from this position on how many. Okay, so from this position on, we do however many. And I say if I fill 0, then from this position on, I have however many, right? And once we come back, empty should be part of it, right? Empty should be part of it. So which means from this on, I have that many ways to fill until index gets too big, right? Okay. Have that many ways to do until it gets too big. I think we can just do dp index plus low. But where do you return plus 1? db plus dp, not plus low, 0, right? Plus dp index plus 1 and plus 1. Plus 1 because I want to say at the current position I can do nothing. Okay? I don't have to add. So if we do this, that will be too much. That's not too much. Oh my god, this is not what I had expected. Oh Lord. Index reach above high, because 0 and 2, right? Index become 3, then that means it's too much. I was actually going to also minus, because it's 3 to 3, right? It's this I was hoping, because if dp 0, let's trace through this whole thing, right? If I go dp 0, then we do dp 1, right? And then we do dp 2, then we do dp 3. And dp3 will give us 0. So dp3 is nothing. So dp2, right? If you dp2, which means you at the 2 position. If you're at the 2 position, 0, 1, 2, you are at a 2 position. And you need to add. Maybe it's larger than. Okay, this one makes sense, right? Which means you can add 1, then you become this. That's fine. All right, then we do dp 0 up until high, and then we can do memo. Let's do memo index all the way to high. So we can say 0 times high plus 1. Okay, and we say we don't have to return this. Is if this just return 0, that's fine. Okay, if this, right? And if let's put -1 to start with. If memo index is smaller than 0, okay? If memo index is smaller than 0, then memo index set to 0, and then, well, probably should just directly do this. Memo index equals to this. And now we return memo index. Okay, so now we can print memo. That doesn't make any sense. I set memo index equal to some value. Why would memo? Oh, because you didn't call DP first. We call DP 0. Okay, and then we return memo. Memo high minus memo low minus 1. Hold on. We're almost there. DP index is from this and towards a high. Okay, so towards the high. Now we want to know is, okay, so from 0 towards this high, right? And then this is start from 0, this start from 1. Hold on. Almost there. What I want to do, right? Is start something, right? Start from 0, and I want to know with high at this position how many, with high at this position how many, and I shall be able to do it, right? Yes, I will be able to do it because this is a start from 0, right? And then we have length 1, length 2, and length 3. This is start from 1. We have length 1, length 2, length 3. So what I want to do is start from 0 with length 2. How do you calculate that? Start from 0 with length 2. Start from 0 with length 2. Or you can say start from 0. Right? I want length 3. So from 0 with length 1, I want to remove that, right? And start from 0 with length 2, I want to remove that. We start from this, right? Hold on. The memo and the DP means different things, okay? It means different things. What we want is starting from index towards the high, how many we have. Therefore, start from index, right? So start from index 0. We can have length 1, length 2, length 3, length 4, and length 5. No, length 1, length 2, length 3, all in this. This is starting from position 1, okay? We have length 1, length 2, that's it. Length 1, length 2, right? So if we have starting from 0, okay? We're saying starts from 0, length 1, 2, 3 have 15 different ways. And we say start from 1, length 1 and 2, we have 7 different ways. Does that mean starting from 0, length 3 is the difference between these two? I mean, it does work, right? But I have to prove it. So we have starting from length 1. So we have 3 positions, right? Yeah, we have 3 positions. The maximum is 3. And then we say starting from this position, length 1 plus length 1 plus length 2 add together, we have 7 different ways, which is true. It's just like, 0, 0, 0, 1, right? 1, 0, 1, 1, and 0, 1. 0, 1, and empty, and empty. So 1, 2, 3, 4, 5, 6, 7. Wait, hold on. How is it 7? Because starting from this position, I can have empty, right? Or I can fill 0, or I can fill 1. Or after I fill this, this can fill 0. This one can fill 0. This one can fill 1. This one. So yeah, these are the 7 different situations. And I know, starting from his position, I have 15 in all. That means what we want is with length 3, I want this position to be filled. Wait, hold on. Why it doesn't work? And I think the DP should change. I think it shall be maybe DPI shall be the number of ways to make what? To make good strings. To make good strings of length I. How about this? We change it, right? So DPI is the number of ways to make length of this. So we can say DP0 is always going to be 1, okay? So DP1 is the number of ways to make 1. DP0 is always 1, and DP1 we have to make 1, which means however much DP0 is, right, from position 0, from position I minus 1, we actually know I minus 0 or I minus 1, right? We check what value that is. And if this is negative, then boo-boo. Otherwise, if it's positive or non-negative, then we can go there to see how many ways there are to make that many, right? And then we add these two together, right? Because if this landing at to a sum index, right, which means there's that many ways to make a string with length this, right? With length this. And then I can do this to make myself. Or I can do this to make myself, right? Then we have these many ways. Therefore, what we are saying is we're going to change the DP. This doesn't change, but this change is not index. We're going to call it length, right? No, actually, no. DP is this, right? In fact, DP0 is always going to be 1. And then we're going to say for I in range 1 to high plus 1. For each one, we say DPI, right? Actually start from 0. DPI shall equal to DPI minus 0, right, plus DPI minus 1. And of course, this has to be multiplied by int I minus 0 is larger or equal to 0. Otherwise, you cannot. And this is the same thing, multiplied by int I minus 1 is larger or equal to 0. So once we do that, and we of course also have the mod. So that's with the length this, how many different ways we can make into length this. And once we're done, we can probably print DP and just take a look. And that will be DP high minus DP low minus 1. Dude. Not right. dp high is how many with length 3? Okay, so high is 3. dp low, so no, it's from low to high, right? So we shall say return for j in range low to high plus 1, right? We're gonna say dpj, and I'm gonna sum these, and then we do mod. All right, now let's see if this one passes. This one passes well. What do you think? I think we spent a long time on this. I'm not happy. Probably need to make it more explicit. dpi is the number of ways to make a good string to make a string of size of length I. All right, do we have that's edge case? 1111, right? That's an edge case. Okay, let's try this. Oh man, half an hour. This is not hard. Well, mainly because the initial dp was wrong, right? I was thinking about it wrongly, and the second attempt was right. What was my previous? Look at this crap. Yeah, the initial dp was not right. That's why it took so long. The first dp attempt was not correct. I was making dpi, right? I was making dpi the number of ways to create string starting from position I. However, that will not help with the size of the string. The second attempt changes the dp such that dpi, right, is the number of ways to create string of size I, right? This way, the dp relation is very clear. dpi is equal to dpi minus 0 plus dpi minus 1, right? That will work, provided that I minus 0 and I minus 1 are non-negative. Okay, let's take a look at what we did last time. This is the fast one. This is the slower one. Oh, it's slow because just because I did not. Oh, that's, dude, I have no clue why you did that way. Low to high. We just need to mod along the way. That's all. Yeah, it's very straightforward. dp mod for if yeah, it's the same. Yeah, I don't know why it took me so long. It doesn't make any sense. It's an easy one. All right, now let's get back to this. Number 9. Let's take a look. That was yesterday. I mean, we solved it based on that. What was this runtime? Didn't really say. Okay. We first sort tasks by the end. For the task with the closest end time, the best strategy is to finish it as late as possible. That way, we have the best chance for the computer time to be reused by tasks which is aligned and mark the computer on slots. When we process a task, we count on slots within the interval. If we still need additional time to finish, we pick available slots starting from binary indexed tree. Wait, hold on. They have fewer for loops. Wait, what is this count? I still don't understand, like the expression here. With the closest end time. So anyway, we'll sort. Okay. And we go through task one by one after sort. Start, end, and duration. Count. What is this count? Do you have a translation? All right, let's translate it. Line. I think that's my consumed. Sort. For this in task. For t in range. The time. D minus equal to. D minus equal to line t. We have start to end. Okay. D minus equal to line t. T equals E. Oh, D minus line. I know what this one does. This is if any one has been processed. If anything has been processed, then you can be processed as well. And while D larger than 0. If not, that's exactly the same, but is this the same? I mean, for me, they use a line. What did you do? So what their mind is, we start from the end and then we try to consume, right? We try to finish everything, and as we consume, we mark on line. We say these times has been consumed. And then, in my case, I just said while t, and I go through everything. I think it's the same. I think it's the same, right? T not in consumed. If not in consumed, we add it, right? So consumed, yeah, this is consumed. And then we go through every single task, right? And for each one of them, I will deduct it. So I think it is the same. We're just doing it differently because I am pre-computing it ahead of time. So when it actually hits it, I will skip it. Right, so that's that idea. To get a number of on slots. Okay, let's see how this one works. I should say I think this is exactly the same idea as solution 1, but seems to have a better implementation. Yeah, this line is interesting. This line. Consumed. I still do consumed, but I think that's a good idea to use 0 times 2001. Yep, that's a good idea. And then we'll sort. Okay. And we say for start and duration in tasks. Okay. So we will check if any time points have been consumed. If so, we can deduct from the current task's duration, because when that time point has been consumed previously, the current task could have been done in parallel as well. So we say for I in range start to e plus 1, d minus equal to consumed I, right? And then we say t equals e, or better yet, yeah, let's go say t equals e, and while d, right, if not consumed t equals 1, and d minus equal 1. If it is, then t minus equal 1 until all consumed. And then we'll return some consumed. Index out of range. How is it possible? Consume the 2000. T is equal to E. T minus equal 1. D minus equal 1. Huh. Interesting. Some has not been consumed. If not consumed T, right? I'll set it to 1, which means it's been consumed. This one minus equal 1. And we go back. T minus equal 1, right? We go back, and then we check the next one. That is interesting. That's very interesting. And which one? I got an issue. 820. while d is larger than 0. Did we just skip? Oh. Oh, here. If not d, break. And then while d. There we go. Isn't this cleaner, right? So on, and then this is the range, times this plus this. Oh, much better. I feel it's the same idea, but why would this one be so much faster? This is the same as this loop. It's just while in this loop, I do this loop. But here I do this loop. Are you saying this loop ends? That is actually true. Because if like this is a hard loop, you'll always have to go through every single time. This can end earlier, but then we can end earlier here. I mean, this is just a loop within a loop. Maybe that's why it's kind of slow. Plus, we're also using a set, right? That's might add some overhead. Yeah, because every time you add, that has a hashing going on. Here is much faster. Okay. So now he says, there's a way to use bit, a mutable prefix sum, to get a number of on slots. Ah, I see. So you don't have to add them up. Just every time you can just do this. I don't feel like it. But you can do this. Right? Yes. Yes, the prefix sum. And then you go through everything. If it has not been consumed, how do you know it's not been consumed? You do this to know it's not been consumed. And this position is 0, then you add it. Oh. I don't think it's going to be faster, but we'll leave it as it. I mean, if this gets really big, then yes, because this portion can be simplified. Because what we want to know is from S to E, how many consumed, or how many of these have been consumed. So we want to know the sum of this interval, right? And we can use this to get the interval, which is perfectly fine, right? We can use this to get the interval, the prefix sum, not prefix sum, the sum within this range, the range sum, right? We can get a range sum, so we do that. And then we need to check if the current time point has not been fulfilled. And to check that is to do this. It's not been fulfilled, so we add it. Oh. Yeah, I'm not going to implement it, but still have to marvel at it. It's really good. Really good. Okay, so move on distribute money to maximum children. What is that? You're given an integer, money, denoting the amount of money that you have, and another integer, children, denoting the number of children that you must distribute the money to. You have to distribute the money according to the following rules. All money must be distributed. Everyone must receive at least $1. Nobody receives $4. The maximum number of children will receive exactly $8. Wait, what? If you distribute according to the aforementioned rules. All money must be distributed, okay. Everyone must receive at least $1. Okay? Nobody receives $4. These some wacky rules, man. Alright, so we have $20. Okay? We have $20 to start with. We have 3 children. We say at least everyone has to have 1 and nobody can have 4. Then we're asking exactly $8. So let's say if we have everybody is $8, that's 24. So we need to remove $4 from them, right? Remove $4. So we can try to remove from 1, then this becomes 4. So we say, can't do that. So we need to remove from another one. So we say we remove 3 from this and remove 1 from this. It becomes 7. And this one become 5. So the answer is 1. That is very interesting. Okay, so the strategy is every child gets 8. Okay, every child gets 8. Then we calculate the total, right? So we have a total, and then if this total is holy crap, it depends. If the total is smaller equal, if the total is equal to money, then we're good. If the total is smaller than money, then we'll do children minus 1, because we can dump whatever the rest onto 1 child. If the total is larger than money, then we need to reduce, and then we can try to reduce from 1, right? And depends on how many more we have, because we have 8 only. So we shall do total minus money, right? We have to do div mod, right? I have to div mod this, and this one would tell me whatever the quotient is, right? The quotient, and we have the remainder. Now the quotient means we have to take away that many from the children completely, right? Div mod this with 8, and we have to take away all of those, and then we have the remaining. Now the remaining, we need to see if the remaining equal to 4, then we have to take away another one. Otherwise, okay, so that is the trick. Gotcha. 91. I think this is right. Okay, so we say total equal to children times 8. If total is equal to money, return children. If total is smaller than money, return children minus 1. Now total is larger than money, then quotient R equals to div mod total minus money and 8. And if R, then we shall return children minus Q minus R equal to 4. Because R equal any other, we can just remove it from that person. Then it's fine. Hold on. Q is the one we have to do. Actually, Q minus 1, right? Because you have, ooh, what if the remainder is 0? Dude. So if R is 0, then we return children minus Q. That's it. Okay. If R is not 0, then we need to do So if r is 0, so r is not 0, right? Minus int r is not 0. So like if r is 0, then we just minus 0, right? And minus this. So if r is 0, this is 0, this is 0, both are 0, right? If r is 0, both are 0, so that's true. If r is not 0, then we have to remove 1, like for sure, which is the remainder 1. And we have to also remove if this is if the r is equal to 4, right? If r is equal to 4, then we have to, because you will say that we remove this, but it's 4. So like this one has to be removed, but it cannot be 4, so we have to remove another one. And we have to say res equal to this, so we shall return res if res is larger than 0, else minus 1. I don't think it's possible to have 0, right? Actually, it's a good question. I don't know. Can we have 0? Can we have the answer be 0? Like, I don't know, have 1 children, right? That's not possible. Children has to be, Jesus, 2 to 30, so 2 children. Okay, yeah, it's easy. We just make it what would be the case when it's impossible if I have 2 child? Too few, right? Too few. 10. Oh, 10 we can fill. Less than 10. 1. Well, 2. Right? Then the total minus money is 2. Total is 16. 16 minus is 12 or 14. 14 8 will be 1. Remainder. Yeah, this is a good try. Output minus, you can do 0. Huh. If there's no way to distribute the money. Oh, we still have a way to distribute the money. Dang it. Hold on. So we have Q and R. R is remainder, right? So children minus Q. So these has to be removed. Oh, but you cannot remove them because everyone has to have at least 1. Shoot. Oh. So, okay, let's rethink about it. Your total money, right, minus this is the extra, right? So you need to remove these extra. So how do you remove these extra? You should divide by 7, right? It's not 8. You should divide by 7. And when you divide by 7, you have the quotient. So you have these 7. We remove 7, remove 7, remove 7. And after remove all of 7s, then we have the remainder, right? And then the remainder, it cannot be 3, right? If it's a 3, then we have to do another one. That shall be 3. Oof, let's try this. But now rest is, we can do 0, right? We can do 0. So if it's negative, maybe that's the case. If it's negative, hold on, let's get all the test case. 1 and 2, right? That is an impossible case. The first one's wrong. 1 2 1 2 0 minus 1, 2 2 0 minus 1. Dude, this is an easy problem. Why is it so hard? 23 shall be 1. 16, 2 shall be 2. Yeah, that's an easy case. 2 2 shall be 0, right? 1 2 shall be minus 1. Money and the children. Distribute money. Wait, 2 1 2 0 1 2 0 minus 1. 1 2 0 1 2 0 minus 1. Oh, I should be larger equal to 0. Right. Okay, the first one. What the hell? What's Q and R? Q is 0 is 4, right? 4. And children is 3. And R is 4. Children minus Q. Children is 3. 3 is 3. Minus 1 is 2. Minus... It should be 4, right? We div mod 7, but the remainder should be 4. Because div mod 7 is we remove the last one. Yeah, it should be 4. That shall be 4. Alright, let's try this. Just try it. Oh my god. I knew it. I didn't really quite understand the expected 0, and I got -1. So 5. Money is 5. 2 children, 16, right? Then 16 minus 5 is 11. 11 mod 7 is 1. Mod 4. Right? 1 mod 4. So children minus 1 is 1. Minus... Hold on. Q, right? So we do all the Q, and then we have this, right? And but the R is... That's why I said it's like it's not about R, it's about the remaining, right? It's about the remaining. Now the R is 4. So I take 1 away. So I take 7 away, right? So 1 is 1. And the other one need to take 4 away. Because I total only have $5. I have 5 and I have 16. So with 8 and 8. So first take 7. And the second, because I have 1, right? And the second I need to take 4. So shall be 4. Oh, and I can redistribute. Dude, you can redistribute. Yeah. So you take them away, take. And you finally end with a 4. And it doesn't really matter because you can always give the other one, right? Yeah, you take 7, 7, 7, and you have the remainder, and we want to avoid having $4, right? So if it is 4, then we need to see if there is another one left to distribute a 4. Right? If it's a 4, it can always distribute. Right? You can always distribute. So unless there's no other for you to distribute, like one is 8, the other is, no, it's just 4. 12, right? 12. If you have $12 and 2 people, $12, 2 people, and $12, 2 people, 16. 16 minus a 4, you're remaining 4. And you divide 4. And that's a good case. What's 12 and 2? That is a 0. Because this is a 4. And you have nothing, no one to distribute it for you. So in that case, in order to not make it 4, you will have to have whoever is 8 to distribute it for you, right? So this is for sure, right? Because these has to be removed. And now we say if the quotient is not equal to 0, then we have to remove at least one more, right? We have to at least remove one more. Now we say if it is, so we have to remove at least one more if it's not equal to 0, right? Have to remove at least one more. And then we say if it's a 4, right? Because when you remove from 8. So we say if r is equal to 4, right? If it's equal to 4, that means we have to check if, yeah, that means we have to remove one more, right? We have to remove one more child. The result is the remaining children, okay? Remaining children now with 8, right? Remaining children with 8. So if it's 4, then if I have something, then we can say if this and not and q is equal to 0, which means I have nobody else to share the burden with me, then rest into minus equal 1. And then I do this. Oh my god. And I just thought about it. 12 and 2. Let's see if this one works. Okay. 走你. Lord. This one's not easy. Yeah, this one's not easy. The analysis of the case where giving each child $8 surpass the total number of money is quite dense. Alright, so this is the case. So if r equal to 4, we cannot directly remove from a child because that child would be left with $4, which is not allowed. In this case, we can share the burden, right? Share the burden of the removed $4 between, right? Because we should remove these $4 and we can wait, hold on. How did you share? Right, we need to remove these $4. Those 7 are removed, right? And this we need to hold on. This is not right. What do you mean? Like if Q is not equal to 0, then it's fine. But we need to remove these $4. And everybody else has been removing $7. So you remove 7, 7, 7, and I choose you need to remove 4. But you cannot remove 4. So you say, I remove, oh, you remove 5. And then you put 1 somewhere else. Yes. In this case, if we have removed $7 from some previous child, instead of removing $4, we can remove $3. Now we can remove $5 on the current child, right? And $6 on the previous child. Thus, we won't hurt the remaining $8 children, unless there are no other child who has $7 removed. In that case, we have to hurt one of the $8 child. Yeah. Dude, this is nah, it's not a bad one. It's just a lot of analysis. This is a good one. Yes. Okay. This is a good one. This is a good one. Divide by 7. Anyway, so yeah, took a while. What's the acceptance rate for this one? Curious. Oh my. Oh yeah, 18%. Dude. Oh well, it was funny. Alright, I chuckled. Okay, that'll be it. I'll see you guys tomorrow. Adios.